So the next part is to work out the error bars on the graph. Now you might actually find it helpful to do this before you place the line of best fit and do the gradient, but you also might find that it doesn't really make much difference. Either way, you need. So the error bars themselves on the graph, if you've got a plotted point, should extend in the x direction and the y direction. We just use a little eye shape to show the top and bottom of the bar. It's worth noting that if, when you add an error bar, it's actually not big enough to plot on the graph, then you can still represent the errors on the graph. So for instance, if we've got voltage and length, if I work out the error bars and they can be plotted to be seen, that's fine. That's what I should do first. And I'll need to calculate an error bar for every point. However, if the error is too small to really plot as an error bar, it couldn't be seen without sort of zooming in hugely and it still seems to be that big and you just can't really view it. Tiny is okay, but if it's not possible to plot the plus or minus on the scale that you've got, then what you should do is take the worst error bar. So you've calculated the size of them all, but put the biggest as a plus or minus on the graph axis. So make sure that you've got the unit, you've got the quantity, but a plus or minus on the axis will take the place of the error bars. You can do that for one of the axes or both. You could, for instance, have the voltages being plus or minus on the axis, but for the lengths, you could have an error bar. So you can do any combination. You can't use the plus or minus on the axis as a shortcut. If your error bars are plottable, then they need to be placed on the axis. They need to be placed on the graph. You can't just put them on the axis. Okay, so we are looking for something ultimately that's going to look like that. So let's have a little look at how we do each one. For voltage, because it's a repeat reading that was used to take or to find a mean value, what you need is the standard error in the mean. And this is the standard deviation divided by root n. N is the number of repeats. If you go back to the first lecture from week 1 and look at the notes in uncertainties, it will talk about how to do standard deviations and standard errors back then. But just as a little bit of a reminder, this is the equation you want to be using. So effectively what you do is you take each value of repeat. So if you've got 6 repeat readings for one set of voltages at one length, you do the difference between each and the mean, you square them, you add them together, you divide by, in this case, 6 minus 1, if you've got 6 repeat readings, so divide by 5, and then square root the whole thing. And that gives you the standard deviation. To get the standard error, you'd then take that and divide that by root 6. Now, it's worth noting that it's absolutely fine if you do all the rough work in your book, but as part of the assessment, what we need to see is one fully explained calculation for every type of calculation that you do. So we would need to see a calculation example for the mean, but we'd also need to see at least one standard deviation shown properly, i.e. put the equation, put a little heading to say what it is that you're doing, show one full amount of working and then an answer. You don't need to do that for every single one, but every type of equation, that's one thing you need to make sure you include. So that would then give you the error bars in V, unless they come out to be too small to plot, in which case just take the worst value and put it as a plus or minus on the axis. The other problem you might have with this method is, what if the error bar, delta V, equals 0? Well, you can't have a 0 error. In these cases, just use the raw data. Now what we mean by that is, in your table, you would have had, for example, lengths, currents, voltages, probably multiple voltages. In each of these headings for raw data, you should have had a unit and an uncertainty. So for voltage, if your voltages all read something like 1.21, then the level of precision is 0.01. So the uncertainty would be half of that, which would be plus or minus 0.005. So you've got to look at your data and decide what your uncertainty would be. If the standard error gives you an uncertainty of 0, then you can just use the raw data uncertainty instead. But you must have an uncertainty. And remember, if that's big enough to plot on the graph, it has to be plotted as an error bar. But if it's not, you can put it in the axis. Okay, so that's voltage. What about length? Uncertainty in length. This is a little bit easier because there's no repeat readings here. So all you've got to do is look at what the uncertainty in your raw data was. Again, if that's big enough to plot on the graph, given your scale, you must plot it. Don't get mixed up between units. If your uncertainty was recorded in millimetres or centimetres, but your length axis is recorded in metres, you must make sure you're trying to put the uncertainty in the same value. Otherwise, you're going to end up with really big error bars when your errors are not remotely that big. So make sure the units match. Volts for volts, metres for metres. And that's all you should be dealing with. You shouldn't be dealing with millivolts or centimetres at this stage.